Look at this. Just look at it, the Roman Colosseum, standing for nearly 2,000 years. A structure so immense, so enduring, it still takes our breath away today. But have you ever truly stopped to wonder how? How did an empire without steel, without modern machinery, without computers, create something that has withstood earthquakes, wars, and the relentless passage of time itself? It's a question that has puzzled historians and architects for centuries. And it speaks to a secret, a lost knowledge buried in the dust of history. This isn't just about old stones and ancient ruins. It's about a sophistication we are only just beginning to fully appreciate. This is the mystery we are about to unravel together. Picture yourself as a Roman engineer. You have no diesel-powered cranes, no reinforced concrete as we know it, no digital design software. Your world is one of human muscle, animal power, and the raw materials of the earth. And yet, with these seemingly simple tools, you are tasked with building an empire. An empire connected by roads that arrow straight across continents, supplied by aqueducts that leap over deep valleys to bring fresh water to thriving cities, and defined by monuments intended to last for eternity. The ambition is staggering. The achievement feels almost impossible. They didn't just build for their own time, they built for a future they would never see, leaving behind a legacy etched in stone for us to discover. So how did they do it? What were the hidden principles, the ingenious tricks, the revolutionary materials that allowed them to achieve the impossible? This is our journey. We are going to dive deep into the world of ancient Roman engineering secrets, to pull back the curtain on the greatest builders the world has ever known. We will uncover the story of a revolutionary concrete that actually gets stronger underwater, explore the precise geometry that allowed their arches to support impossible weights, and decode the logistical genius that organized an entire empire. This is more than a history lesson. It's a detective story. It's a quest to understand a level of human ingenuity that continues to humble and inspire us. So join me as we step back in time, to walk the dusty forums and bustling construction sites of ancient Rome, and finally discover the astonishing secrets behind the structures that defined the ancient world. To understand their genius, we have to start with the very stuff of their empire, concrete. But this wasn't just any concrete. What the Romans developed was nothing short of a miracle material, a technological marvel that we are only now, 2 millennia later, truly beginning to comprehend. While our modern concrete is designed to last for decades, maybe a century, Roman concrete was engineered for millennia, and the most incredible part, it actually gets stronger when exposed to seawater. At the heart of this ancient alchemy was a special volcanic ash known as pozzolana, named after the town of Pozzuoli near Mount Vesuvius, where it was first quarried. The Romans discovered that by mixing this fine, reactive ash with lime and water, they created a paste of astonishing durability. But the real magic happened out at sea. When building harbors like the one at Portus Cossanus, they would combine this pozzolana lime mortar with chunks of volcanic rock aggregate, and then deliberately submerge the whole mixture in seawater. To any modern engineer, this seems like a catastrophic mistake. Seawater is the enemy of modern concrete, slowly corroding the steel reinforcements and causing the material to crack and crumble. For the Romans, however, seawater was not the destroyer, it was the catalyst. The chemical reaction that follows is a process scientists are still unraveling. When seawater percolates through the concrete, it interacts with the volcanic ash and lime to form rare, crystalline minerals. One of the most important is a strange-like mineral called aluminous tobermorite. This isn't just a passive filler. It's an incredibly strong, plate-like crystal that reinforces the entire matrix. Think of it like the skeleton within the concrete, a super strong structure that grows and interlocks over time, literally knitting the material together from the inside out. The seawater doesn't weaken it. It provides the essential ingredients for this long-term chemical reaction, allowing the concrete to self-heal tiny cracks as they form. A Roman pier submerged for 2,000 years isn't just surviving the waves. It is continuously becoming a more resilient version of itself. This stands in stark contrast to the concrete that builds our modern world. Our formula, based largely on Portland cement, is inherently less complex and more brittle. It lacks the ability to adapt and strengthen in the face of environmental stress. Instead, it slowly degrades, requiring constant and expensive maintenance. The quest to understand the Roman secret has become a major scientific endeavor. Teams at universities around the world are using advanced tools like electron microscopes and X-ray microdiffraction to analyze ancient Roman samples, atom by atom. They aren't just historians, they are materials scientists reverse engineering a 2,000-year-old patent. The goal is breathtakingly ambitious: to create a modern version of this concrete. Imagine a new generation of seawalls and breakwaters that could fortify our coastlines against rising sea levels. Structures that wouldn't erode, but would instead grow tougher with every passing storm. Or consider the implications for storing hazardous waste, encasing it in a material guaranteed to hold strong for thousands of years, not just hundreds. The Romans, in their relentless pursuit of permanence, may have inadvertently left us the blueprint for a more resilient future. They solved a problem we are still grappling with today, and the answer was buried not in a scroll, but in the silent, enduring chemistry of their harbor walls. But if their concrete was the revolutionary foundation, then the Pantheon's dome was its ultimate masterpiece. This is not just a roof, it is an architectural area sung in stone and light, a structure so advanced that its secrets continue to confound engineers to this day. Let's be clear about what we're dealing with here. Nearly 2,000 years after it was built, the Pantheon still holds the record as the world's largest unreinforced concrete dome. Just let that sink in for a moment. In an age of computer modeling and carbon fiber, no one has ever dared to build a dome of pure concrete this vast without steel bars to hold it together. The Romans did it with rudimentary tools and a profound, almost intuitive, understanding of physics. So how does it stand? The answer is a breathtakingly clever series of engineering solutions, each one designed to outsmart the immense forces of gravity and compression trying to pull the dome apart. The most obvious genius is right at the very top, the oculus, that great open circle, 9 meters across, flooding the interior with a shifting beam of sunlight. It's often described as a symbolic eye to the heavens, which it is, but it is also a critical structural component. By removing the heaviest part of the dome, its center, the engineers massively reduced the overall weight, and more importantly, the outward thrust that would have threatened to make the walls buckle. It acts as a natural stress reliever, a calculated void that maintains the dome's integrity. But the ingenuity doesn't stop there. Look closer at the dome's composition. The Romans understood that you don't need the same heavy, robust material at the very top of the arch as you do at the base, where all the weight is bearing down. As the dome rises, the concrete mix changes. At the very bottom, the aggregate or the filler mixed into the concrete is massive, heavy basalt rock. But as your eye travels upward, that aggregate gradually becomes lighter and lighter. They began mixing in progressively porous volcanic stone like tufa and pumice, and by the time you reach the majestic oculus at the apex, the concrete is almost entirely made of light, airy volcanic pumice. It's a breathtakingly elegant gradient of weight, a perfect marriage of material science and architectural form. Then there are the coffers, those 140 beautifully recessed squares that pattern the interior. We admire them for their aesthetic harmony, but they are far more than decoration. Each coffer is a carefully calculated act of subtraction. By carving out all that excess material, the builders lighten the dome's load even further without sacrificing an ounce of its structural strength. It is the architectural equivalent of drilling holes in a titanium bicycle frame. You remove only what isn't needed, creating a structure that is both stronger for its weight and infinitely more elegant. All of this rests upon walls that are not merely thick, but intelligently thick. The drum of the Pantheon is 6 meters of solid brick-faced concrete. But even here, the Romans employed clever tricks. Hidden within those walls are a series of relieving arches, redistributing the immense load of the dome down through 8 critical piers and away from the vulnerable spaces in between, like the grand entrance and the niches. Every single element, from the mix of the mortar to the shape of the ceiling, was part of a single, cohesive and brilliant plan to defy gravity for the ages. The Pantheon's dome is not a monument that has simply survived through luck. It stands today as a calculated, deliberate and stunningly sophisticated victory of ancient engineering over the relentless forces of nature. And if the Pantheon shows us their mastery over weight and space, then the aqueducts reveal a command over an even more elusive element, water itself. To provide for their sprawling cities, Roman engineers performed what must have seemed like miracles of hydrology, moving millions of gallons of fresh water every single day across vast, uneven landscapes, using nothing but the silent, relentless pull of gravity. They didn't just move water. They convinced it to flow obediently across valleys and over plains, defying the very lay of the land to deliver life to their people. The entire system was an elegant, gravity-fed network. The principle was simple. Water always seeks its own level, but the execution was breathtakingly complex. It required finding a water source, often a spring or a mountain lake, that was at a higher elevation than the final destination city. The real challenge began with the surveyors. These were the unsung heroes of Roman infrastructure, the mathematicians and engineers who had to plot a course with a gradient so precise, so unerringly consistent, that water would flow steadily for dozens of miles without ever slowing to a stop or rushing so fast it eroded the channel. We're talking about a drop of maybe 1 foot for every mile of distance, a slope so slight it's almost imperceptible to the human eye. How did they achieve such impossible precision without modern laser levels or GPS? Their primary tool was the chorobates, a remarkable piece of ancient technology. It was a long wooden bench, about 6 meters long, with legs at each end and a carefully grooved trough running along its top. The surveyor would fill this trough with water, using the surface of the water itself as a perfect reference for a level plane. To check for a grade, they would use dioptra, a precursor to the theodolite, for sighting angles over long distances. They would painstakingly measure and remeasure, setting up a series of aligned posts over the proposed route to ensure the gradient remained constant, mile after mile after mile. Of course, the land itself was rarely a flat, obliging surface. When the surveyors encountered a deep valley, they didn't reroute the aqueduct around it, they built across it. This is where we see those iconic, soaring arcades of stone that have become synonymous with Roman engineering. These were not just for show. They were the most efficient way to maintain the water channel's crucial elevation and gradient across a depression. The arches were the perfect structural form to support the immense weight of the water, filled conduit on top, transferring the loads gracefully down to the foundations. In some cases, like the Pont du Gard in southern France, these structures were so perfectly engineered that they stand completely intact today, without a single speck of mortar holding the stones together. The precision of the cut and the balance of the forces did all the work. Once this water arrived in the city, it wasn't just dumped into a reservoir. It was distributed through a complex, pressurized network of lead and terracotta pipes to public fountains, lavish bathhouses, and even the homes of the wealthy. The abundance of clean, running water was a cornerstone of Roman public health and civic pride. The great baths were not merely places to get clean. They were social hubs, cultural centers, and a powerful statement about what Roman civilization could provide for its citizens. The constant flow from public fountains ensured that even the poorest inhabitants had access to fresh water, a luxury unheard of in many parts of the world for centuries to come. This was engineering in the service of society, a tangible demonstration that the empire's greatest strength was its ability to improve the daily lives of its people. Yet for all the life-giving power of their water systems and the soaring majesty of their domes, the true backbone of the Roman Empire was not found in its cities, but in the ground beneath its soldiers' feet. We are talking, of course, about the roads. These were far more than simple dirt paths. They were the iron ligaments of empire, a vast and sophisticated network of stone and ingenuity that bound a continent together. The famous proverb, "All roads lead to Rome," was not just a saying, it was a statement of logistical, military, and economic fact. These highways enabled legions to march at stunning speed to crush a rebellion, allowed goods and ideas to flow from Egypt to Britain, and created a sense of unified identity across a sprawling collection of cultures. Their construction was a meticulous, layered process, a testament to an engineering philosophy that believed even the ground we walk on should be built to last forever. The genius of a Roman road was in its foundation, quite literally. They didn't simply level the earth and lay down stones. They built a multi-layered, subterranean masterpiece. The process began with the fossers, the ditch diggers, who would excavate a trench about 1.5 meters deep. Into this trench, they would lay the stotumen, a foundation layer of large, flat stones packed with rubble. This base was crucial for stability, especially in wet conditions, as it prevented the road from sinking into the soft ground below. On top of this, they added the rudis, a thick layer of crushed rock mixed with lime mortar, which acted as a firm, load-bearing cushion. The next layer, the nucleus, was often made of a finer mix of sand, gravel, and quicklime, packed down hard to create an incredibly solid and level surface. Finally, on top of all this hidden engineering, came the surfacing, the summer cruster. This was the visible, walking surface made of large, interlocking polygonal blocks of hard volcanic stone like basalt or flint. These stones were expertly cut and fitted together so tightly that a knife blade could scarcely slip between them. This wasn't just for show. This tight fit prevented the stones from shifting under the constant pounding of cart wheels and marching boots, creating a remarkably smooth and durable surface. But the sophistication didn't stop at the layers. The road's surface itself was a marvel of hydrological design. It was never flat. Instead, it was built with a distinct camber, a gentle convex curve that arched from a high point in the center down to gutters at the sides. This brilliant feature meant that rainwater would never pool on the surface. Instead, it would instantly run off into the drainage ditches that flanked every major road, keeping the foundation dry and stable, and the traveling surface mud-free in all weather. This attention to water management, a recurring theme in Roman engineering, ensured these roads were passable year-round, turning seasonal tracks into permanent, reliable arteries. This network of all-weather highways fundamentally changed the tempo of empire. A Roman legion, burdened with heavy packs and equipment, could march over 20 miles in a single day on these stone-paved roads, a speed that was unheard of in the ancient world. This rapid deployment allowed Rome to project its power over immense distances, responding to threats with an efficiency that kept its enemies perpetually off balance. But the roads were not just for soldiers. They carried olive oil from Spain, wine from Gaul, and precious spices from the east, directly into the heart of the empire. They carried ideas, letters, and innovations, shrinking the vast Mediterranean world and weaving diverse provinces into a single interconnected economic and cultural unit. The Roman road was more than a path. It was the physical manifestation of the empire's unifying will, a strip of carved stone that announced Rome's order, its efficiency, and its absolute determination to endure. This architectural revolution all hinged on a single, beautifully simple shape, the arch. While the Romans didn't invent the arch, they were the first civilization to truly understand its potential and wield it as the fundamental building block of an entire empire. Before the Roman arch, grand structures were primarily built with a post and lintel system, think of Stonehenge, or the Pantheon in Greece, with massive horizontal beams resting on top of vertical columns. This method created beautiful buildings, but it had a severe limitation. The space inside was always cluttered with columns needed to support the heavy roof, and the weight of the entire structure created immense downward and outward pressure, limiting the scale of what could be built. The Roman arch elegantly solved this problem by redirecting forces in a completely new way. The genius is in its curved shape. When a load is placed on top of an arch, the weight doesn't just travel straight down. Instead, it gets transferred down the curve of the arch and outward to the sides, creating what engineers call a lateral thrust. This is the force that wants to push the legs of the arch apart. The Roman breakthrough was understanding that this outward thrust had to be contained. They did this with massive, sturdy walls or buttresses at the sides of the arch, effectively locking the entire structure into a state of perfect equilibrium. The stones in the arch, known as voussoirs, are literally squeezed together by the weight above them, a principle called compression. The entire structure becomes stronger under load, each stone holding its neighbor in place. The final crucial piece is the keystone, the central wedge-shaped stone at the very top of the arch. When the keystone is dropped into place, it completes the structure and locks all the other voussoirs into their positions, making the arch self-supporting. This mastery of the single arch was just the beginning. Their true innovation was in repetition and combination. By placing a long series of arches side by side, they created an arcade, the defining feature of their aqueducts and bridges. This design was incredibly efficient. It used far less material than a solid wall, allowed wind and water to pass through during floods, reducing pressure on the structure, and could span vast distances with a graceful strength that still feels modern. Then they took this concept into the third dimension. By extending an arch along a line, they created the barrel vault, essentially a continuous arched tunnel. This allowed them to roof over enormous spaces like the public halls in basilicas or the corridors beneath an amphitheater. But the barrel vault still had a weakness. Its downward and outward thrust was continuous along its entire length, requiring massively thick, strong walls on both sides to contain the pressure. Their solution to this was one of their most brilliant architectural innovations, the groin vault. This was created by taking two barrel vaults of the same size and intersecting them at a perfect right angle. The intersection created a series of arched lines, or groins, that channeled all the weight and thrust down into the four corners of the vault. This was a game changer. By concentrating the forces onto four specific points, The groin vault eliminated the need for continuous, solid walls. The spaces between the support points could now be opened up, filling a building with light and air. This principle was pushed to its absolute limit with the development of the dome, which is essentially an arch rotated 360 degrees on its axis, channeling forces in a perfect circle down to its base. The arch, the vault, and the dome, these were the tools that allowed Romans to sculpt space itself, creating the vast, uninterrupted interiors that defined their imperial grandeur. Yet these monumental roads, aqueducts, and buildings all began not with stone, but with a vision, a precise plan laid out on the landscape itself with an accuracy that seems to defy their technological era. This is where we encounter the true unsung heroes of Roman engineering, the surveyors, the agrimensors. Armed with a toolkit of ingenious, if seemingly simple, instruments, these master measurers could imprint the rigid order of Roman design onto the most chaotic and unforgiving terrain. Their ability to chart a perfectly straight road across a forested hill, or set the gradient of an aqueduct with a drop of mere inches per mile, was the indispensable first step in every project, the silent arithmetic that made the grand spectacle possible. The most iconic of their tools was the groma, a device of elegant simplicity designed for one critical purpose: establishing perfectly straight lines and right angles. Picture a vertical staff with a horizontal crosspiece rotating at the top. From each of the four arms of this crosspiece, a plumb bob hung on a string. The surveyor would plant the staff firmly into the ground, and then carefully rotate the crosspiece until one pair of plumb bobs aligned precisely with a distant marker stake. Once set, the two arms perpendicular to this line would give two new sight lines that were exactly 90 degrees to the first. With this one instrument, a team could lay out the entire grid plan of a military camp, or the relentless straight course of a road like the Via Appia, ensuring its unwavering path across the Italian countryside for hundreds of miles. It was a tool that embodied the Roman worldview: order, discipline, and unwavering straight lines imposed upon nature. But while the groma mastered direction, it was the chorobates that mastered the even more delicate art of level. We mentioned this instrument briefly with the aqueducts, but its sophistication deserves a deeper appreciation. The chorobates was a wooden bench, often about 6 meters long, with legs of identical length at each end. Along the top of the bench was a precise groove that the surveyors would fill with water. The still surface of this water provided a perfect reference for a true level plane. For even greater precision, especially on windy days when the water might ripple, the chorobates was also equipped with a set of plumb lines hanging from each end. By aligning these lines with marks etched onto the bench, the operator could achieve an incredibly accurate reading. This tool was nothing short of vital. The success of an aqueduct, whose gradient could be no more than a gentle one in 2000, depended entirely on the chorobates. A single error in leveling over a long distance could mean the water would flow backward or simply stagnate in the channel, rendering the entire multi-year, immensely expensive project utterly useless. The chorobates was the guardian against that catastrophic failure. Beyond these two key tools, the Roman surveyor's toolkit included other clever devices. The dioptra was a more complex sighting instrument used for measuring horizontal and vertical angles, essentially an early theodolite, and for simply measuring distance, they relied on the dependable disempeda, a 10-foot rod that was the standard unit for their meticulous land measurements. It's crucial to understand that using these tools was a slow, painstaking, and highly skilled process. A team establishing the route for an aqueduct would have to move the chorobates forward, inch by inch, taking a measurement, then moving the instrument again and repeating the process over 50 miles of uneven ground, all while ensuring their cumulative error was negligible. It was a monumental exercise in patience and precision. This profound understanding of measurement and geometry allowed them to execute projects that still baffle us with their accuracy. The tunnels for aqueducts and roads, dug by crews starting from opposite sides of a mountain, would meet in the middle with near-perfect alignment. The foundations for massive structures like the Colosseum were laid perfectly level, a necessity for supporting such immense and asymmetrical weight. The tools themselves were made of wood and bronze, materials susceptible to warping and wear, which means the true genius was not just in the instruments, but in the meticulous skill and unwavering standards of the people who used them. They transformed simple concepts of water and weighted string into the invisible framework of an empire, proving that precision is not a function of technology, but of discipline, intellect, and an uncompromising commitment to getting it right. Yet for all their grand public works, perhaps the most intimate and telling example of Roman engineering genius is found not in a sprawling forum or a soaring aqueduct, but in the very floors and walls of their homes and bathhouses. In a world without forced air furnaces or electric radiators, the Romans engineered a system of central heating so effective, so luxurious, that it would not be widely replicated in Europe for more than 1500 years. This was the Hypocaust, a word that literally means fire beneath, and it represents a breathtakingly clever manipulation of heat and airflow that turned the bitter cold of winter into a distant memory for those who could afford it. The principle was elegant in its simplicity. A furnace or prefurnium was stoked continuously by slaves or servants, often located in an external room to keep the smoke and soot away from the living spaces. But this fire didn't just heat the air around it. Its heat was captured and channeled. The real innovation was the raised floor. The solid floor of a room was supported by a grid of short, sturdy pillars made of stacked clay tiles or stone bricks, creating a hollow space or plenum about 2 to 3 feet deep. The hot gases and smoke from the furnace were directed into this underground chamber, where they would swirl and circulate, effectively turning the entire floor into a massive radiator. The heat would then slowly, steadily, conduct through the layer of concrete and tile above, warming the room from the ground up in a gentle, even wave. But the Romans didn't stop at the floor. Understanding that heat rises, they further engineered the walls to become part of the system. Embedded within the walls were rows of rectangular hollow tubes made of terracotta, called tubuli. These box flues were carefully stacked and mortared together, creating continuous vertical channels from the hypocaust chamber below all the way up to the roof. As the hot air from beneath the floor rose, it would naturally draw through these wall cavities, ensuring that not just your feet were warm, but that the very air around you was consistently heated. This brilliant design prevented the walls from becoming cold surfaces that could condense moisture and create damp, making the rooms not only warm but also dry and healthy. The exhaust from this entire system would eventually exit through vents in the roof or specially designed chimneys, ensuring a constant draft that pulled fresh heat from the furnace through the entire network. The most sophisticated application of this technology was in the vast public bath complexes, like the baths of Caracalla in Rome. These were not simple buildings, they were thermodynamic masterpieces. A complex series of furnaces would heat different rooms to precisely different temperatures. The frigidarium or cold room was unheated. The tepidarium was a warm lounge, gently heated by the hypocaust to a comfortable temperature. The real showpiece was the coldarium, the hot bath. This room was often positioned on the south side of the building to capture the sun's warmth, and was heated aggressively by its own dedicated furnace. The floor here could become almost too hot to walk on without sandals, and the water in the large plunge pool was kept scalding hot by a heated metal tank above the furnace, known as a testudo, or by running water through pipes that were baked by the furnace's flames. The entire process was a carefully orchestrated ballet of fire, water, and air, all managed without a single thermometer or pressure gauge, relying instead on accumulated empirical knowledge and skilled stokers. The luxury this system provided is almost difficult to overstate. In the depths of a British or German winter, a Roman patrician in his villa could stroll on warm floors in bare feet. The marble and mosaics pleasantly heated against his skin, while the wind howled outside. The public baths offered every citizen, from the wealthy senator to the common soldier, a refuge from the cold, a place to socialize, conduct business, and cleanse oneself in unparalleled comfort. The fuel cost was enormous, requiring vast quantities of wood or charcoal, which made the Hypocaust a powerful symbol of status and wealth. Its eventual disappearance following the fall of the Western Roman Empire stands as a stark indicator of the loss of that complex technological knowledge and organized economy. For centuries afterward, European winters were endured huddled next to smoky, inefficient open fires. The memory of evenly radiated heat fading into little more than a legend until the modern era rediscovered the very principles the Romans had mastered so long ago. Of course, the heaviest stones and most elegant arches are meaningless if you cannot lift them into place. This brings us to one of the most visceral and awe-inspiring aspects of Roman construction: their revolutionary crane technology. We must completely discard any image of simple ropes and levers manned by countless slaves, straining against impossible weight. The reality was far more sophisticated. The Romans engineered a range of powerful mechanical hoists, the most impressive of which were powered by the most abundant engine they had: human perseverance, channeled through a deceptively simple machine known as the treadwheel crane. The heart of this system was the massive wooden wheel itself, a structure that could be as large as 5 or 6 meters in diameter. Inside this wheel, like a hamster in a cage, a team of men would walk steadily forward, their collective weight and motion turning the entire apparatus. This was not a task for the weak. It was grueling, precise labor. But by converting their linear walking motion into a powerful rotary force, the treadwheel created a mechanical advantage that a simple team of men pulling on a rope could never achieve. The real magic, however, was in the gearing. The axle of the great treadwheel was connected to a much smaller drum via a series of stout wooden gears. For every single rotation of the large wheel, the smaller drum would spin multiple times. This meant that while the men walked at a slow, sustainable pace, the rope attached to the drum would wind up at a much faster rate, allowing for controlled and relatively swift lifting of enormous loads. The true lifting power, however, was born from a brilliant understanding of pulley systems. Roman engineers didn't just use a single rope over a wheel. They mastered the compound pulley, a concept often attributed to the genius Archimedes, but perfected and applied on an industrial scale by the Romans. A typical Roman crane would employ a set of 3, 4, or even 5 pulleys, known as sheaves, mounted in a block. The rope would be threaded through this entire system. The mechanical advantage gained is exponential. A 5-sheave system, for example, means that the force required to lift a load is only a fraction of its total weight. While the men in the treadwheel might be exerting, the collective force needed to lift, say, 2 tons, the pulley system would allow them to hoist an object weighing 10 tons or more. This wasn't just about raw power. It was about managed power, allowing a small team to move massive objects with precision and control, placing a multi-ton stone block onto a delicate arch with the careful placement of a master craftsman. Evidence of these incredible machines is etched into the stones themselves. Look closely at the blocks of Roman monuments. and you will often find a series of distinctive deep, U-shaped grooves cut into their sides. These are not decorative, they are the marks of the iron claws of the crane, known as Lewis irons. This was another brilliant Roman innovation. A dovetail-shaped hole would be carved into the top of a stone block. The Lewis iron, a set of 3 interlocking pieces of forged iron, would then be inserted into this hole. As the crane took the weight and began to lift, the central piece of the Lewis would be forced outward, wedging the 2 side pieces tightly against the stone. The harder the crane pulled, the tighter the grip became, allowing the block to be lifted securely without any risk of the ropes slipping. Once the block was perfectly positioned, a simple release mechanism would allow the Lewis irons to be withdrawn, leaving behind only those small, telltale grooves as a permanent signature of the machine that put it there. The scale of what they achieved with this technology is almost incomprehensible. The columns of the Pantheon's portico, each a single piece of granite weighing over 40 tons, were quarried in Egypt, shipped across the Mediterranean, and then lifted into place in the heart of Rome using these cranes. The massive stone blocks that form the apex of triumphal arches, often positioned dozens of feet in the air, were all set by the coordinated effort of men walking inside these great wooden wheels. This system was the linchpin of their entire construction speed. It allowed them to build with a velocity that matched their ambition, erecting colossal structures in years rather than decades. The rhythmic, steady turning of the treadwheel was the heartbeat of Roman construction, a perfect symphony of human effort, wooden mechanics, and iron will that literally raised an empire from the ground up. This relentless drive for efficiency and overwhelming force defined not just their construction sites, but their battlefields as well. For a Roman legion on campaign, engineering wasn't a specialized side project. It was a daily survival skill, as fundamental as wielding a gladius or raising a shield. Every single afternoon, no matter the terrain or the weather, a legion would stop its march and perform what seemed like a magic trick. They would conjure a heavily fortified, defensible town from absolutely nothing. A complete fortress built in a matter of hours. This was the castrum, the standardized marching camp, and it was the ultimate expression of Roman military discipline and engineering pragmatism. The process was a well-drilled ritual, executed with a speed that must have been demoralizing to any local tribes watching from the surrounding hills. As soon as the commanding general selected a suitable site, preferably high ground with access to water, the entire machine would snap into action. The first men on the scene were the surveyors, the metators, who would use their gromers to lay out the entire camp's blueprint on the ground. They would mark the location of the 2 main streets, the Via Principalis and Via Praetoria, which crossed at the center, and the precise outline of the 12-foot high earthen rampart that would define the camp's perimeter. This wasn't a haphazard arrangement. Every single camp, from the hills of Scotland to the deserts of Syria, was built to the exact same logical, grid-like plan. A soldier transferred from one end of the empire to the other could wake up in the middle of the night in a new camp and know instantly where the headquarters tent, the hospital, or his own unit's section was located. This uniformity bred incredible efficiency and eliminated confusion. Then every single man, from the lowliest auxiliary to the commanding legate, had a job to do. Some would begin excavating a deep, V-shaped ditch around the entire perimeter, piling the excavated earth inward. Behind them, another team would pack that earth into a formidable rampart, reinforcing it with the sod bricks they had just cut from the turf. Meanwhile, others would venture out to nearby woods to cut timber, sharpening the ends of thousands of stakes to create a deadly palisade along the top of the rampart. The legions even carried a special type of saw, designed to be operated by 2 men, that could rapidly fell trees and process lumber. Before the sun had even set, the legion would be safe behind a ditch, a wall, and a spiked fence, with their tents neatly arranged in orderly rows, a bakery already operating, and a fully functional field hospital ready for casualties. This nightly ritual transformed the army from a vulnerable column on the march into an impregnable fortress, allowing them to rest securely in the heart of hostile territory. It was a psychological weapon as much as a defensive one, a constant demonstration of Roman order and invincibility. But when the Romans were the ones laying siege, their engineering genius shifted from disciplined defense to overwhelming, terrifying offense. To break into enemy fortifications, they developed a terrifying arsenal of artillery machines that were the ancient equivalent of precision bombardment. The two most famous were the ballista and the onager, and while they are often grouped together, they served very different purposes on the battlefield. The ballista was a sophisticated torsion weapon that functioned like a massive crossbow on a tripod. Its power came from two vertical bundles of tightly twisted sinew or horsehair, into which were inserted two wooden arms. When the machine was winched back, these arms strained against the torsion of the twisted ropes. When released, they would snap forward, hurling a large, iron-tipped bolt with devastating accuracy and velocity. This was not a weapon for smashing walls. It was an anti-personnel sniper rifle. A well-trained crew could fire these heavy bolts in a relatively flat trajectory, capable of skewering multiple enemy soldiers in a row or picking off defenders from the battlements with horrifying precision from hundreds of meters away. For the job of actually battering down gates and shattering masonry, the Romans relied on the onager, whose name means wild ass, for its powerful and unpredictable kick. This was a simpler but far more brutal machine. It used a single enormous horizontal torsion spring, a massive bundle of rope, and a single stout throwing arm inserted into it. The arm was winched down against this incredible torsion, often using a large capstan turned by several men. When the trigger was released, the arm would slam against a huge, padded buffer at the front of the frame, launching a massive stone or a clay pot filled with burning pitch in a high, arcing trajectory over the enemy wall. The onager was the area effect weapon, the siege breaker. The crash of a 50-pound stone landing on a wooden tower, or the explosion of flaming pitch on a thatched roof inside the fortress created chaos, terror, and destruction, softening the defenses for the final assault. The Romans didn't just use these machines in isolation. They employed them in coordinated batteries, with ballistae suppressing the walls while onagers pounded the same section repeatedly, systematically degrading the enemy's will and their defenses until the legionaries could advance with their siege towers and battering rams to finish the job. This combination of relentless process and terrifying innovation gave the Roman army a tactical edge that few of its adversaries could ever hope to counter. Yet for all their might on land, the true test of Roman engineering ambition was not found on solid ground, but at the chaotic, shifting meeting point of sea and shore. To feed their empire and project their power, they needed to conquer the coastline itself, creating safe havens for their massive grain ships and mighty warships where nature had provided none. This challenge required them to perform what must have seemed like literal magic. They learned to build in the sea itself, constructing colossal artificial harbors that defied the relentless power of waves and tides. The crown jewel of this maritime engineering was Portus, the great artificial harbor of Rome. A project so vast it dwarfed nearly all others and showcased their absolute mastery over the watery element. The primary obstacle was the Mediterranean's fury. A traditional breakwater made of loose stone, no matter how large, would eventually be pounded to rubble by storm waves. The Romans' revolutionary solution was, once again, their supernatural hydraulic concrete. But here, its application was pushed to its absolute limit. They didn't just use it to make piers. They used it to create immense monolithic barriers right on the seafloor. The process was a breathtaking feat of logistics and bravery. First, massive wooden caissons, essentially huge box-like forms, were constructed on barges and then carefully sunk into position to outline the desired breakwater or pier. Then the daring work began. Teams of divers, likely using little more than weighted lines and their own lung capacity, would guide the pouring of the concrete mix, the pozzolana ash, lime, and aggregate directly into these submerged wooden forms. The result was not a pile of stones, but a single, continuous, rock-solid mass that became one with the seabed. As the seawater interacted with the pozzolana, it triggered the chemical reaction that caused the concrete to cure and grow stronger over centuries, not weaker. These underwater concrete walls could absorb the incredible energy of storm surges without cracking or shifting. At Portus, they created a massive, hexagonal inner harbor basin, surrounded by these concrete quaysides, where hundreds of ships could unload their cargoes of Egyptian grain, Spanish olive oil, and Syrian glass in perfect safety, protected from the open sea by a mighty concrete breakwater and a strategically placed lighthouse. This wasn't just a port, it was a machine for empire, a perfectly engineered node in the global supply chain that kept 1 million citizens in Rome fed and content. Guiding those precious cargo ships safely into these engineered havens was the final critical link in the chain, the lighthouse. The most famous of all was the Pharos of Alexandria, one of the 7 wonders of the ancient world. And while it was originally built by the Ptolemaic Greeks, the Romans adopted, perfected, and replicated its design across their empire. A Roman lighthouse was not a simple bonfire on a tower. It was a sophisticated optical and architectural system designed to project light over staggering distances. The tower itself was a marvel of stability, often built on a massive concrete foundation sunk into treacherous coastline rocks to prevent shifting. The structures rose in a tapering circular or square design, with incredibly thick walls at the base to withstand both the weight above and the constant battering of salt spray and wind. At the very summit was the lantern room, the true heart of the operation. Here, a large, constant fire burned, likely fueled by resinous wood or coal to create a bright, intense flame. But the Romans didn't just rely on the raw power of the fire. They amplified it using a principle we still use today: reflection. Behind the fire would have been a large, polished bronze mirror, curved to act as a reflector. This ingenious device would capture the light that would normally radiate uselessly in all directions, and focus it into a powerful, directed beam aimed straight out to sea. On a clear night, this concentrated beacon could be seen from dozens of miles away, a piercing man-made star cutting through the darkness to give sailors their first shore landmark after weeks of open water. It told them not just that land was near, but exactly where a safe, deep water channel began and where the deadly hidden rocks lay. The Romans built these guiding sentinels at all their major ports, from Dover in Britain to Leptis Magna in North Africa. They understood that engineering was not just about brute force and structure. It was about providing information, safety, and certainty. The combination of the unsinkable concrete harbor and the unmissable beam of the lighthouse created a complete system of maritime safety. It reduced the enormous risks of ancient sea travel, encouraged commerce, and allowed the Roman navy to deploy and respond to threats with a speed and reliability that kept the Mediterranean for centuries as a Roman lake. These structures were more than just functional. They were powerful symbols of order and civilization, beacons of hope, literally shining Rome's promise of safety and technological mastery into the treacherous darkness of the unknown sea. Now consider for a moment what the world was like before clear glass. Windows were merely open holes in a wall, perhaps covered with animal hide, thin sheets of stone like mica, or wooden shutters. These solutions offered protection from the elements, but plunged interiors into a perpetual gloom, making buildings dark, drafty, and damp. The revolutionary idea of filling that opening with a transparent solid, of harvesting daylight while blocking the wind, was a quantum leap in human comfort. And while the Egyptians and Mesopotamians had been creating beautiful glass objects for millennia, their craft was dedicated to opaque beads and vibrant vessels. The Romans were the first to crack the code on transparency and produce glass on a scale not for mere luxury items, but for architectural use, literally bringing a new light into the ancient world. This breakthrough was born from a combination of empire-wide resource gathering and industrial innovation. The key ingredient for glass is silica, which they had in abundance in the form of pure white sand, particularly from the riverbanks near Ravenna. To this sand they added a flux, a substance that dramatically lowers the melting temperature. While other cultures used soda ash, Roman glassmakers in regions like Galilee began experimenting with natron, a naturally occurring salt harvested from dry lake beds. This natron-rich mixture, when fired in their incredibly hot furnaces, produced a more stable and often clearer glass. But the true secret to clarity lay in the addition of manganese dioxide. Roman artisans discovered that this mineral, when introduced to the molten mix, acted as a decolorizer. It neutralized the green or blue tint caused by iron impurities in the sand, resulting in the coveted colorless, transparent vitrum that could be formed into panes. The manufacturing process itself evolved to meet the colossal demand of the empire. They moved beyond small batch production to something approaching an industrial operation. One of the most common methods was glassblowing, a technique thought to have been invented in the Syrian region of the empire around the 1st century BCE. This allowed them to create a stunning variety of shapes quickly. For windows, however, the preferred technique was casting. They would pour the molten glass into flat, open molds made of stone or packed sand to create rough, thick sheets. Another ingenious method was the cylinder-blown technique. A glassblower would create a large, elongated bubble of glass, which was then slit lengthwise while still hot and carefully flattened out in a kiln, creating a larger, thinner, and more uniform sheet. These panes were not perfectly clear by our modern standards. They often contained tiny bubbles, waves, and a slight hazy tint. But for a Roman stepping from a dark corridor into a room illuminated by such a window, the effect must have been nothing short of miraculous. The impact of this innovation on Roman architecture and daily life was profound. For the first time, architects could design spaces with reliable, permanent sources of natural light. In the sprawling public bath complexes, vast windows filled with these translucent panes illuminated the steaming pools and grand halls, creating an airy, luminous atmosphere that enhanced the sense of civic luxury. In the homes of the wealthy, particularly in colder northern provinces like Britain, glass windows became a highly prized feature. They transformed living spaces, allowing sunlight to warm and brighten rooms throughout the day while keeping out the cold and rain. This was a dramatic improvement in quality of life, reducing dampness and the reliance on smoky oil lamps during daylight hours. It even changed the very aesthetics of interior design, as wall paintings and intricate mosaics could now be seen in their full intended brilliance. This embrace of transparent glass stands as a powerful testament to the Roman core values of improving daily life and mastering the environment. It was a technology that served both practical comfort and breathtaking beauty. From the humblest villa window to the sun-drenched grandeur of an imperial bathhouse. They looked at a common material and saw not just its potential for decoration, but its power to transform the very experience of space itself, allowing them to capture and hold the daylight in a way no civilization had ever done before. And if their mastery of the arch defined their buildings, then their application of it over water stands as one of their most daring and enduring achievements. To connect their vast empire, Roman engineers had to conquer rivers, not just cross them. This required a completely different kind of thinking, moving beyond dry land to tackle the dynamic, powerful challenge of flowing water. Their bridges were not mere crossings. They were permanent declarations of Roman authority over nature itself, combining the elegant theory of the arch with raw, ingenious construction techniques that allowed them to build foundations in the most impossible of places, the bottom of a rushing river. The first and most formidable obstacle was the river itself. How do you build the foundation for a massive stone pier in the middle of a deep, fast-moving current? The Roman solution was the cofferdam, a temporary enclosed structure that allowed them to create a dry worksite right on the riverbed. The process began with workers driving two concentric rings of sturdy wooden piles into the river bottom, forming a circular or rectangular wall. The space between these two walls was then packed tightly with clay, forming a waterproof seal. Once this bathtub-like structure was complete, the real work could begin. Using a series of water wheels or buckets operated by a continuous human chain, they would relentlessly bail out the water trapped inside the cofferdam. This was back-breaking, dangerous labor, a constant battle against the river trying to reclaim its space. But once the water was removed, engineers and stonemasons could descend into this temporary dry chamber to excavate the riverbed down to solid rock and begin laying the pier's foundation courses, all while the river surged harmlessly against the outer clay wall. With the foundation secured, the true artistry of the bridge could rise above the waterline. Each pier was a monument to stability, designed with a sharp, angular cutwater on both the upstream and downstream sides. This triangular form was a brilliant piece of hydrodynamic engineering. It didn't just resist the current, it sliced through it, dramatically reducing the pressure on the pier during floods, and deftly guiding debris like logs and rubble around the structure instead of allowing it to pile up and cause damage. Upon these mighty, river-defying piers, the Romans then built their signature arches. But these were not the relatively small arches of a city aqueduct. These were monumental, awe-inspiring spans of stone that leapt across the waterway with breathtaking confidence. The weight of the bridge and any traffic on it was converted by the arch into a downward and outward thrust, which was then channeled directly down through the heart of the pier and into the solid foundation they had so painstakingly built on the riverbed. The entire structure was a single, cohesive unit, perfectly balanced against the forces of gravity and water. Perhaps no bridge exemplifies this perfect marriage of daring engineering and sublime artistry better than the Alcantara Bridge in Spain. Crossing the deep gorge of the Tagus River, it is a structure that still inspires disbelief. Its builder, Gaius Julius Lacer, left a permanent inscription on the bridge itself, Pontem perpetui manserum in secula, meaning, "I have built a bridge which will last forever." It was not an empty boast. Completed around 106 CE, the bridge stands nearly 60 meters above the river, a testament to Roman ambition. Its 6 towering arches, hewn from massive granite blocks, are a masterclass in precision. The largest arch spans an almost unbelievable 35 meters. What is truly staggering is the minimalism of its design. The entire roadway is just 8 meters wide, a slender ribbon of stone that achieves its strength not from bulk, but from the perfect geometry of its arches and the impeccable placement of each stone. It has withstood 2 millennia of floods, wars, and even deliberate attempts to destroy it, standing today not as a ruin, but as a fully functional monument to its creator's skill. The enduring legacy of these structures is not just in their stones, but in their very purpose. A Roman bridge was a permanent investment in the future, designed to require minimal maintenance and to serve generations yet unborn. They were the critical nodes in the vast network of roads, ensuring that the legions, the couriers, and the merchants could move in all weather, at all times of the year. This unshakable connectivity was a primary source of Roman power, allowing them to administer a vast territory with an efficiency that would not be seen again in Europe for over 1,000 years. When you stand before the Alcantara Bridge, or any of the hundreds of lesser-known Roman bridges still carrying traffic today, you are not just looking at a clever arrangement of stone. You are witnessing the final, triumphant step in a long battle against a powerful river. A battle won not with force, but with intellect, perseverance, and an unwavering belief in the power of engineering to shape the world. Now, all of these engineering triumphs, the concrete, the arches, the cranes, they all converged in one ultimate monument of Roman ambition and ingenuity, the Colosseum. We see it today as a majestic ruin, its massive stone skeleton open to the sky. But to truly appreciate its genius, we have to mentally rebuild it, to see it not as a static monument, but as a dynamic, complex machine. This was not just a building designed to hold 80,000 people. It was a building designed to put on the greatest, most spectacular, and most terrifying shows on Earth. And to do that, it required a level of backstage engineering that rivals the backlots of modern Hollywood. The real magic, the true heart of this brutal theater, was hidden from the spectator's view. Beneath the wooden floor of the arena lay a dark, labyrinthine world known as the Hypogeum, meaning underground. This was a 2-level subterranean city of brick and stone, a chaotic backstage area where the spectacle was manufactured before being unleashed upon the sand above. It was a network of narrow passageways, holding pens for hundreds of exotic animals, lions from North Africa, bears from Germany, elephants from India, all kept in darkness before their terrifying ascent into the blinding sunlight and roar of the crowd. Gladiators would wait here too, preparing for combat, or perhaps waiting to be lifted up in elevators to meet their fate. The elevators. This is where Roman engineering becomes almost unbelievable. The Hypogeum was equipped with an intricate system of around 80 vertical shafts, each capped by a wooden platform that could be raised to arena level. These were not simple hoists. They were sophisticated counterweight-operated elevators, powered by teams of slaves manning massive capstans. The system was a masterpiece of coordinated chaos. Through a series of tunnels, animals and performers could be moved from their holding areas to the base of these shafts. The capstan would be turned, the ropes would tighten, and a trapdoor on the arena floor would suddenly burst open as a tiger or a group of gladiators was dramatically revealed to the screaming audience. This allowed for breathtaking special effects. Warriors could appear as if from nowhere, and wild beasts could seemingly materialize in the center of the action. The entire Hypogeum was a carefully orchestrated machine for delivering surprise and suspense, controlling the narrative of the games with mechanical precision. But the engineering marvels weren't confined to the world below. Above the heads of the crowd was another staggering innovation, the velarium. Picture a massive canvas awning, larger than a modern football field, designed to shade 80,000 people from the harsh Roman sun. Deploying this colossal sail was a logistical puzzle of immense proportions. It was not a single piece of fabric, but a series of overlapping segments, and it was operated by a dedicated unit of sailors from the Roman naval fleet at Misenum, the only men with the specialized rope handling skills for such a task. The mechanics were breathtaking. A network of ropes radiated out from a series of stone corbels, or projecting supports, at the very top of the Colosseum's outer wall. These ropes were attached to the outer edge of the velarium. Another set of ropes, controlled by teams of men on the ground using huge winches, ran through pulleys on those same corbels. To deploy the awning, the sailors on the ground would slowly let out the winch ropes, allowing the heavy canvas to unfurl outward from its mast at the top of the structure. It was a delicate balancing act, requiring perfect coordination to ensure the enormous cover spread evenly without tearing. When retracted, the entire system was gathered neatly against the attic story of the building, a testament to its elegant design. This was climate control on an unprecedented scale, a thoughtful piece of civic engineering that demonstrated a concern for spectator comfort amidst the otherwise brutal displays. The Colosseum was a building of stark contrasts, unimaginable violence below, and a shaded, comfortable experience above, all made possible by the most advanced technology of the ancient world. It stands as the ultimate symbol of Roman engineering, a perfect fusion of raw power, breathtaking spectacle, and meticulous, problem-solving genius. Yet the stone roads and soaring monuments would have meant little if the cities themselves were chaotic, unsanitary, and difficult to navigate. Here, the Roman genius shifted from grand structures to the very organization of daily life, demonstrating that true civilization is built not just on spectacle, but on order, cleanliness, and public health. While the Greeks are often credited with the concept of the grid city, the Romans perfected it and applied it with an unwavering, systematic efficiency across their entire empire. This wasn't merely about aesthetics. It was a tool for military control, economic prosperity, and social management. The blueprint for this order was the castrum, the military marching camp, but rendered in permanent stone and mortar. When establishing a new city, Roman surveyors would first identify the central point, the crossing of the two main streets, the north-south Cardo Maximus and the east-west Decumanus Maximus. These were not simple paths. They were broad, colonnaded thoroughfares designed for wheeled traffic, commerce, and public procession. From this central crossroads, a perfect grid of smaller streets was laid out, creating uniform city blocks known as insulae. This rigid planning created a predictable, easily navigable city. A stranger could be given an address and find it without difficulty. More importantly, it allowed for the efficient movement of troops to quell unrest and the logical zoning of space for residential, commercial, and industrial purposes. At the heart of this grid, both physically and symbolically, was the Forum. This was the true center of Roman urban life, a grand public square surrounded by the most important buildings, the Basilica for law and commerce, the Curia for city governance, and temples to the protective gods of the city. The Forum was the living room of the city, a space for politics, shopping, socializing, and ceremony. This careful allocation of space for public use reflects a profound understanding of civic well-being. It was a deliberate creation of a shared identity, a place where the community could come together and function as a cohesive whole. This model was replicated from the damp frontiers of Britain to the deserts of North Africa, creating a sense of Roman identity no matter how far from the capital a citizen might be. But the most revolutionary aspect of Roman urban planning lay not in what was above ground, but in what was hidden beneath it. While their contemporaries were dumping waste into open trenches or simply into the street, the Romans were building one of the most advanced public health systems the world would ever see until the modern era. The crown jewel of this system was the Cloaca Maxima, the greatest sewer. Its origins are almost mythical, begun in the 6th century BCE, under the rule of the Etruscan kings. Initially, it was little more than an open ditch designed to drain the swampy water from the valley between Rome's hills into the Tiber River. Over centuries, the Romans transformed this simple channel into a monumental, vaulted subterranean canal, large enough for a boat to row through. This was no mere ditch. It was a feat of engineering. Built from massive blocks of volcanic tuff and later lined with waterproof hydraulic concrete, the Cloaca Maxima collected wastewater from public latrines, bathhouses, and even the homes of the wealthy, carrying it away from the populated city center. Its construction required immense effort, with workers tunneling beneath the city and diverting streams to ensure a constant flow that would flush the system and prevent blockages. The system was so effective that parts of it remain in use to this day, a testament to its incredible construction. The impact of this engineering on public health cannot be overstated. By efficiently removing human waste and stagnant water, the Romans drastically reduced the incidence of waterborne diseases like cholera and typhoid that plagued other ancient cities. This sanitation network was complemented by an equally impressive supply of fresh water from the aqueducts, creating a constant cycle of clean water in and waste water out. The result was a level of urban cleanliness and population density that would not be seen again in Europe for over 1,000 years after the fall of Rome. This commitment to public health infrastructure reveals a sophisticated understanding of the connection between sanitation and societal well-being, demonstrating that Roman engineering was ultimately in the service of building a healthier, more functional, and more resilient society for all its citizens. Yet for all its incredible durability and the sheer scale of its use, the secret of Roman concrete did not survive the empire that perfected it. With the gradual collapse of the Western Roman Empire and the fracturing of its vast trade networks and specialized knowledge, the precise recipes and sophisticated mixing techniques that created this miracle material faded into obscurity. The great imperial building projects ceased, and the need for such a high-performance, maritime-grade concrete vanished. The knowledge became a ghost, lingering only in the silent, enduring walls of structures like the Pantheon and the harbor at Portus, waiting for a future civilization smart enough to ask how they were still standing. The loss was not instantaneous, but a slow decay of expertise. Master masons and engineers, once trained in a continuous tradition, found their skills no longer in such high demand. The meticulous process of sourcing the specific, reactive volcanic ash from Pozzuoli and mixing it in the exact proportions with lime and aggregate became a forgotten art. Medieval and later builders looked upon these ancient ruins with awe, but they could only replicate the form, not the substance. They attempted to use the same volcanic materials, but without understanding the critical chemistry, resulting in concrete that was a pale, weak imitation of its Roman predecessor. The world had to wait over a millennium for the invention of modern Portland cement. A material we now know is fundamentally inferior in longevity and environmental resilience. The quest to crack the Roman code has become one of the great scientific detective stories of our time. Modern researchers aren't just reading old texts. They are using the most advanced analytical tools at their disposal to reverse engineer the ancient material, atom by atom. Teams from universities around the world take core samples from ancient Roman piers, carefully drilling into structures that have been submerged in the Mediterranean for 2,000 years. Back in the lab, they subject these samples to intense scrutiny using electron microscopes, X-ray diffractometers, and spectrometers. This high-tech archaeology has revealed the concrete's complex nanocrystalline structure. identifying the key role of minerals like aluminous tobamorite and the way the lime clasts within the mix contribute to its self-healing properties. This isn't merely an academic exercise. The potential applications are staggering. A modern concrete that could self-heal its own cracks would revolutionize infrastructure, drastically reducing the astronomical costs of maintenance and repair for bridges, roads, and tunnels. A marine concrete that grows stronger in seawater could allow for the construction of truly durable coastal defenses and offshore energy installations, resilient to the rising threats of climate change and erosion. The Roman formula, with its use of far less energy-intensive processes than modern Portland cement, could also point the way toward greener, more sustainable construction materials, potentially reducing the massive carbon footprint of the global construction industry. The secrets buried in those ancient harbor walls hold the promise of not just understanding the past, but of building a more resilient and enduring future, finally completing a circle of knowledge that was broken for over 1,500 years. But controlling a river for a bridge was one thing. Taming it entirely for human use was another level of hydrological ambition. The Romans didn't just want to cross water, they sought to command it, to store its life-giving force and bend its flow to their will. This brings us to a less celebrated but equally brilliant facet of their engineering, the mighty dam. While we often picture their aqueducts leaping over valleys, it was their dams that created the massive reservoirs those aqueducts drew from, forming the crucial first link in the entire water supply chain. Their approach to dam building was a masterclass in understanding the raw, pushing power of water and designing structures to withstand it for centuries. The most iconic of these structures were the gravity dams, massive barriers that used their own immense weight to hold back the incredible force of a reservoir. But Roman engineers were never content with mere brute force. They always sought an elegant, intelligent solution. Their breakthrough was the realization that a straight wall was not the most effective shape to resist pressure. Instead, they pioneered the use of the curved dam, a design so advanced it seems to defy the era. By arching the dam convexly into the reservoir, they achieved something brilliant. The water's pressure wasn't just pushing straight against a flat wall. It was now channeled along the curve of the structure, transferring the load outward into the canyon walls or the sturdy abutments on either bank. This clever design effectively used the natural topography as a support system, turning the entire landscape into a co-conspirator in their engineering scheme. It was a perfect marriage of form and physics, a shape that literally hugged the water it contained. We can see this genius preserved in stone at sites like the Cornavo Dam in Spain, a structure that is not only still standing, but remains in use after nearly 2,000 years. Built from mortared granite blocks, its curved face is a silent testament to Roman hydrological understanding. The mortar itself was a key ingredient, often a pozzolana-based concrete that would set strong and water-resistant, ensuring the dam wouldn't simply seep itself apart. The care taken in its construction is evident in every fitted stone, a project meant not for a generation, but for eternity. These dams created vast, reliable lakes where none existed before, capturing seasonal rainwater and snowmelt to provide a constant, regulated supply for the cities downstream. Nowhere was this ability to create artificial oases more critical than in the arid provinces of North Africa, modern-day Tunisia and Libya. Here, in a landscape of harsh sun and limited rainfall, the Romans performed what can only be described as hydrological alchemy. They constructed extensive systems of dams and reservoirs to support a thriving agricultural industry that became the breadbasket of the empire. The strategy was comprehensive. Larger feeder dams were built in the highlands to capture flash floods from sporadic rainstorms. This water was then channeled through a network of sluices and canals into vast, open-air reservoirs, strategically located near farming settlements. These reservoirs were the beating heart of the operation. They smoothed out the wild inconsistency of the climate, storing water from the occasional deluge to provide a steady, dependable supply for irrigation throughout the long, dry seasons. The scale was immense. The remains of these systems still scar the North African landscape today, with some reservoirs covering dozens of acres. This engineered abundance allowed for the cultivation of olive groves and wheat fields on an almost industrial scale, producing the oil and grain that were shipped across the Mediterranean to feed the insatiable appetite of Rome itself. It was a stunning transformation, turning marginal lands into some of the most productive in the entire empire, all through the deliberate, intelligent management of water. This wasn't just farming. It was a statement of absolute control over the environment, proving that with enough ingenuity, even the desert could be made to bloom. But this mastery of water wasn't just for sanitation or spectacle. The Romans also harnessed its raw, flowing power to drive machinery on an almost industrial scale, automating arduous tasks in ways that wouldn't be seen again for over 1,000 years. While we often picture the water wheel as a medieval invention, it was in fact the Romans who first deployed it systematically across their empire, transforming the relentless energy of rivers into practical, mechanical force. The most widespread and vital application was in milling grain. For a city like Rome, with a population exceeding 1 million, the daily demand for flour was colossal. Hand grinding with quern stones was simply not an option. It was a task that demanded automation. The evidence for this is staggering. The late Roman writer and court official Cassiodorus describes a single complex on the Janiculum Hill in Rome that was powered by the aqueducts and employed a battery of water wheels to keep the city fed. But the most spectacular example lies not in Italy, but in southern France, at the site of Barbegal near the city of Arles. Here, Roman engineers built what can only be described as an ancient industrial factory. They constructed a massive aqueduct that fed not a city, but a hillside of 16 individual, overshot water wheels, arranged in 2 parallel rows of 8. An overshot wheel, where water is delivered to the top of the wheel, is far more efficient than a simple undershot design, capturing the water's weight in addition to its flow. The aqueduct channeled water to the top of the complex, where it dropped down, sequentially turning each wheel in the first cascade. The water was then captured and directed to the top of the second cascade, turning another 8 wheels. The power output would have been phenomenal. Historians estimate the complex could have produced enough flour to feed the entire population of Arles, estimated at 12,000 people, with a substantial surplus for trade. This wasn't a simple mill. It was a carefully calibrated machine, a symphony of flowing water and rotating stone that ran 24 hours a day, 7 days a week. The rhythmic sound of the grinding stones would have been a constant industrial hum, a testament to Roman engineering's shift from pure monument building to the large-scale production of essential goods. It represents a quantum leap in economic thinking, an early move towards centralized, automated production that foreshadowed the factories of the modern industrial age. Yet their mechanical ingenuity extended far beyond grinding wheat. Archaeologists have uncovered evidence of water power being applied to a stunning variety of tasks. There were water-powered saws for cutting stone and marble, a brutally difficult job that was revolutionized by converting the rotary motion of a water wheel into a back and forth motion for a saw blade. This allowed for the precise and rapid cutting of stone blocks and even decorative marble veneers, greatly speeding up construction and reducing the immense human labor required. There is also compelling evidence, from the writings of Vitruvius and later Roman engineers, for water-powered trip hammers. These machines would have used cams mounted on the axle of a water wheel to repeatedly lift and drop heavy wooden hammers. This technology could have been used for a multitude of purposes: for fulling cloth, where the hammers would pound and felt woolen textiles; for crushing ore in mining operations; or even for processing hemp and tanning leather. The true enabling technology behind many of these machines was the Roman mastery of gearing. They perfected the use of both simple and complex gear trains, primarily using sturdy oak and bronze. The crown gear, which allows for a change in the axis of rotation, was particularly crucial. This meant the horizontal rotation of a water wheel's axle could be transferred into the vertical rotation needed to turn a millstone. They also understood the principle of the gear ratio, using a large gear to turn a smaller one, thereby increasing the speed of rotation for tasks that required it. This sophisticated understanding of force, torque, and motion transmission allowed them to adapt the raw power of a water wheel to an array of different tools, creating what were essentially the first programmable machines. By simply changing the configuration of gears and cams, the same flowing water could saw wood, pound cloth, or crush ore. This represents a conceptual leap from seeing technology as a tool for building things to seeing it as a system for doing things, a fundamental shift toward mechanization that planted the earliest seeds for the world we live in today. While they were masters of stone and water, the Romans also possessed a profound, almost intuitive understanding of something far more elusive: the physics of sound itself. In an age without microphones or speakers, ensuring that a single actor's voice or a musician's lute could reach every one of the thousands of spectators in an open-air theater was an acoustic challenge of the highest order. Their solution was not a matter of magic or happy accident. It was a meticulous science of shape, material, and precise calculation, resulting in amphitheaters where a whisper on the stage could be heard with perfect clarity in the very highest row. The entire design of a Roman theater was, in essence, a giant amplifier carved from the earth. The most critical feature was the semi-circular, steeply raked seating area, the cavea. This bowl-like shape was not just for providing a good view. It functioned as a massive sound collector. The curved surface acted as a continuous series of acoustic mirrors, capturing the sound waves emanating from the stage and reflecting them upward and outward, channeling the energy of the performance toward the audience rather than allowing it to dissipate uselessly into the open air. The steep angle of the seating ensured that each row of spectators was positioned directly in the path of these reflected sound waves, with each tier catching the sound and preventing it from being absorbed by the people below. This careful geometry created a natural sound beam, focusing the audio and dramatically reducing the dilution of volume that normally occurs over distance. The very materials they chose were selected for their acoustic properties. The seats were almost invariably made of solid, dense stone like marble or limestone. These hard, smooth surfaces are highly reflective to sound. They do not absorb acoustic energy, but bounce it back with great efficiency. An actor's voice would hit the stone seats and steps and be reflected back into the listening space, reinforcing the direct sound and adding a slight, sustaining reverberation that enriched the vocal quality without creating a muddy echo. This stands in stark contrast to the construction of the stage building itself, the skene frons. This ornate, multi-storied backdrop was often built with niches, columns, and complex reliefs. These surfaces didn't just serve as beautiful scenery. They acted as a sophisticated diffuser, breaking up sound waves that hit the back of the stage and scattering them back toward the audience in a way that prevented harsh, focusing echoes that could distort the original performance. Perhaps the most ingenious acoustic trick was hidden beneath the very feet of the performers. The stage floor, known as the orchestra, was often constructed not of solid earth, but of resonant wooden planking. Below this wooden stage, archaeologists have found evidence of large, strategically placed ceramic pots or bronze vessels, carefully tuned to specific resonant frequencies. These vessels, called resonantes or équerres, were embedded upside down within hollow chambers beneath the stage, their open mouths facing up toward the performers. They functioned as Helmholtz resonators, a principle we still use in acoustic engineering today. When a singer hit a specific note that matched the natural resonant frequency of one of these pots, the air inside would begin to vibrate sympathetically, amplifying that particular tone and giving the voice a richer, more powerful carrying quality. It was a form of natural sound equalization, built directly into the architecture. The overall effect of these combined techniques is still a marvel to experience today. In well-preserved theaters like the one in Aspendos, Turkey, or Orange, France, modern visitors can test the phenomenon for themselves. A person standing on the stage can speak in a completely normal, conversational tone, and every word will be intelligible to someone sitting in the topmost tier, dozens of meters away and at a vertiginous height. There is no strain, no shouting required. The architecture itself does the work. This commitment to perfect audibility reveals a deep-seated Roman belief that civic architecture should be inclusive, ensuring that the cultural, political, and religious events held in these spaces were accessible to all attendees, regardless of their social status or wealth. The best views and the best sound were not reserved for the elite in the front rows. Through engineering, they were a shared experience for the entire community. A powerful demonstration that in the Roman world, even something as intangible as a spoken word could be mastered and perfected. To fuel their empire of stone, the Romans first had to master the earth itself, venturing deep into the underworld to extract the very bones of their civilization: metal. Their insatiable demand for lead for plumbing, iron for tools and weapons, and copper and tin for bronze drove an industrial mining operation on a scale that would not be matched again until the Industrial Revolution. Their approach was characteristically systematic and brutally efficient, combining immense manpower with a clever, almost violent, application of hydraulic engineering to tear open the landscape and reveal its riches. When a rich ore vein was discovered, often by following surface deposits or through simple prospecting, the first challenge was removing the vast quantity of overburden, the soil and rock covering the valuable deposit. This is where Roman ingenuity truly shone with a technique known as hushing, a form of hydraulic mining that turned water into a destructive tool. They would dam a stream high in the mountains, channeling the water into large storage reservoirs. When a sufficient volume had been accumulated, the engineers would open the sluice gates, releasing a catastrophic, deliberately engineered flash flood directly down the mountainside towards the mining site. This enormous torrent of water would scour away the soil, tear apart soft rock, and strip the hillside bare, exposing the mineral veins beneath for easier extraction. The force was so powerful, it would literally carve new gullies and ravines into the land, scars on the earth that are still visible today in places like Los Majulas in Spain. A breathtaking landscape that is now a UNESCO World Heritage Site. Its jagged red cliffs, a permanent monument to Roman industrial might. But their mastery did not stop at the surface. To follow the veins deep underground, they developed sophisticated methods for tunneling and shaft mining. Using iron picks and wedges, and hammers made of heavy stone, teams of miners would work in shifts by the faint, flickering light of olive oil lamps, carving their way through solid rock. The deeper they went, the more dangerous it became, facing constant threats from tunnel collapses, flooding, and poor air quality. Their solution to ventilation was remarkably clever. They would use a series of fires at the base of auxiliary ventilation shafts. The heat from these fires would create a powerful updraft, pulling the stale, oxygen-poor air out of the mine and drawing fresh air in through the main entrance, creating a continuous circulation that allowed them to work at depths previously thought impossible. Once the ore was hauled to the surface in baskets or leather bags, the real alchemy began. Roman metallurgy was a complex empirical science, a series of closely guarded processes passed down through generations of smiths. For iron, the most critical metal for the military, the process started with the bloomery furnace. This was a chimney-like structure made of stone and clay, packed with alternating layers of iron ore and charcoal. Bellows, often operated by hand or foot, pumped air into the base, stoking the temperatures high enough to melt the rocky impurities from the ore, which would flow away as slag. What remained was a spongy, glowing mass of nearly pure iron mixed with slag, called a bloom. This bloom was then repeatedly heated and hammered on an anvil by a master smith. With each strike, the impurities were forced out, and the iron fibers were welded together, creating a tough, malleable wrought iron that could be shaped into everything from nails and hinges to the deadly points of pilum javelins. For bronze, the alloy of copper and tin used for statues, coinage, and fittings, the process required even greater precision. The metals had to be smelted separately and then combined in a crucible in exact proportions to achieve the desired hardness, color, and casting properties. This was a testament to their advanced understanding of material science, allowing them to create alloys perfectly suited for specific tasks. Perhaps the most shocking scale of production was reserved for lead. Mined in enormous quantities, this toxic metal was the plastic of the Roman world. It was used for waterproofing roofs, for making coffins, and for weights, but its most vital application was in their plumbing systems. The word plumbing itself derives from the Latin for lead, plumbum. They would cast molten lead into long, continuous sheets, which were then rolled into pipes, with the seams soldered shut with more molten lead. This network of pipes, distributing water throughout their cities, was a triumph of mass production and metallurgical skill, even if its long-term health effects were tragically unknown to them. The entire process, from the mountain-scouring rush of water to the final hammer strike on the anvil, reveals an empire built not just on grand ideas, but on the soot-covered, relentless labor of extracting and refining the very elements that made it all possible. Yet for all its breathtaking sophistication, this golden age of engineering did not last forever. The sheer brilliance of Roman construction can sometimes blind us to a sobering historical reality. These techniques, these secrets, were not eternal. They faded, they were lost, and much of Europe entered a period where the very knowledge of how to build in concrete, operate a treadwheel crane, or maintain a vast aqueduct simply vanished from common practice. So what happened? How could such a powerful and deeply ingrained tradition of technical knowledge simply crumble away? The answer is not a single cataclysmic event, but a complex web of interconnected failures that slowly unraveled the very fabric of Roman technological society. One of the most significant factors was the gradual but terminal collapse of the economic system that made such grand projects possible. The empire's unparalleled engineering was astronomically expensive, funded by the immense wealth generated by a stable, continent-spanning economy with efficient trade routes and a reliable tax base. As the 3rd and 4th centuries wore on, this system began to break down. Constant civil wars and foreign invasions disrupted trade and ravaged agricultural land, the primary source of Roman wealth. Hyperinflation, triggered by emperors debasing the silver currency to pay for these endless wars, made long-term financial planning for massive infrastructure projects impossible. The state, which had always been the primary patron of these grand works, found itself increasingly bankrupt, its resources diverted from building aqueducts to raising armies for survival. Without the deep, centralized coffers of a functioning imperial government to fund them, the great building yards fell silent, and the continuous chain of knowledge transmission from master to apprentice was broken. This economic collapse was both caused by and contributed to intense political instability. The era of the so-called barracks emperors in the 3rd century saw the throne change hands with violent frequency, often seized by military commanders from the frontiers who had little connection to or care for the urban heartland of the empire. This constant power struggle meant that long-term visionary projects were abandoned in favor of short-term, desperate defensive measures like quickly shoring up city walls. The capital itself moved from Rome to Milan, and then to Ravenna in the west, and to Constantinople in the east, further fragmenting the centralized authority and the pooled resources needed for empire-wide construction. The empire was effectively split in two, and the eastern half, while wealthier and more stable, began to develop its own architectural traditions, slowly drifting away from the old Roman methods. In the west, the political order simply disintegrated, taking with it the administrative framework that had organized the quarrying, shipping, and construction industries for centuries. As the state fractured and the economy crumbled, the highly specialized knowledge required for these engineering feats became unsustainable. Consider the teams behind a project like the Pantheon's dome, the master architects who understood the complex mathematics of thrust and compression, the surveyors who could level a foundation over miles with a chorobates, the foremen who knew the exact recipe for the pozzolana concrete mix, and the crane operators who could coordinate the lifting of a 40-ton column. This was not common knowledge. It was a tightly held corpus of expertise passed down through generations within specific guilds and workshops. As large-scale projects ceased, these specialists found no work. Their unique skills were no longer in demand, and with no apprentices to teach, their knowledge died with them. The slow, painful transition into what we now call the Dark Ages was marked by a dramatic simplification of life and technology. Societies became localized, agrarian and subsistence-based. The elaborate interconnected system that supplied a city like Rome with African grain, Spanish metal, and Egyptian paper vanished, replaced by small communities struggling to feed themselves. In this new world, there was simply no need for a 50-mile aqueduct or a harbor that could withstand 2,000 years of waves. The ambition itself had shrunk, and with it, the knowledge required to fulfill it was deemed unnecessary and was allowed to fade into history. The great structures they left behind were seen not as inspiration for new projects, but as magical relics from a lost race of giants, their secrets buried too deep for a diminished age to ever recover. And yet, despite this grand fade into history, the ghost of Roman engineering never truly left us. It's not just present in the ruins we admire, it's embedded in the very DNA of our modern world, its principles echoing in the skyscrapers that define our skylines and the materials that build our future. The most direct and powerful link is found in the ongoing revolution inspired by their concrete. For centuries, we thought we had surpassed them with our Portland cement, but we're now humbly realizing they had discovered a more sophisticated and sustainable path. Modern materials scientists aren't just studying ancient Roman harbors as historical curiosities. They are treating them as active laboratories, reverse engineering a 2,000-year-old recipe to solve some of our most pressing modern problems. The discovery of the self-healing properties within Roman concrete, driven by the slow chemical reaction between seawater, lime clasts, and volcanic ash, has become a blueprint for a new generation of materials. Researchers at institutions like MIT and Harvard are developing bioconcretes that contain encapsulated bacteria or healing agents designed to activate upon cracking, mimicking the ancient process. The goal is to create infrastructure that can repair its own wear and tear, drastically reducing the monumental costs of maintenance and extending the lifespan of our bridges, tunnels, and roads. This isn't just imitation, it's evolution, using nanotechnology to achieve what the Romans did through ingenious chemistry, proving their foundational work is more relevant today than ever before. The Roman architectural philosophy, particularly their mastery of compressive force through the arch, the vault, and the dome, remains a fundamental pillar of structural engineering education. Every modern civil engineering student learns the principles of load distribution and thrust that Roman builders applied intuitively and then perfected through practice. The flying buttresses of Gothic cathedrals, which allowed those breathtakingly high, thin walls filled with stained glass, are a direct medieval evolution of the Roman understanding of how to counteract the lateral thrust of a vault. Today, we see this same principle applied in the design of massive dams, where the curved, arched form is used to channel immense water pressure into the canyon walls, and in the thin shell concrete domes of modern sports arenas and planetariums, which achieve vast, column-free spans using the exact same geometric logic that supported the Pantheon. The Roman insistence on building for permanence, on over-engineering for longevity rather than for short-term cost savings, is a lesson modern society is slowly relearning as we grapple with the wasteful cycle of disposable construction. Their structures were designed for a 1,000-year lifespan. Many of our modern buildings are designed for 50. This shift in perspective, back towards resilience and durability, is perhaps one of the most valuable lessons we can take from their example. This influence extends far beyond pure structure into the very way we organize our societies and manage our resources. The Roman holistic approach to urban planning integrating water supply via aqueducts, waste removal via sewers, public health via baths, and civic life via forums established the template for the modern city. When we turn on a tap and expect clean water to flow, or flush a toilet and trust a network of pipes to carry the waste away, we are participating in a system whose core principles were laid down by Roman engineers. Their concept of public infrastructure as a government's responsibility to its citizens, something that improves quality of life for everyone, is a cornerstone of modern civil society. The grid-based layout of their cities, designed for efficient movement and administration, is visibly replicated in the street plans of countless modern cities across North and South America. Even our legal systems surrounding water rights and public access ways have deep roots in Roman law and their meticulous approach to land surveying and property demarcation. Perhaps the most profound connection is not in the specific techniques, but in the Roman mindset itself, a relentless, pragmatic drive to identify a problem and engineer a solution, no matter the scale. They looked at a mountain and saw not an obstacle, but a source of water that could be channeled. They looked at a river and saw not a barrier, but a pathway to be bridged. They looked at the open sea and saw not a limit, but a highway to be secured with artificial harbors and guiding lighthouses. This ethos of confident, ambitious problem-solving is the direct ancestor of the modern engineering spirit that sent humans to the moon and is now working to tackle climate change. The specific tools have changed from the Groma and Corabates to satellite GPS and computer-aided design. But the core mission remains identical. to understand the laws of nature and use them to shape a world that is safer, more connected, and more prosperous for humanity. In every self-healing concrete polymer and in every elegantly arched bridge, the legacy of those ancient builders lives on, not as a forgotten relic, but as a continuous, evolving conversation between the past and the future of human ingenuity. Yet for all their grand public works, perhaps the most intimate and telling example of Roman engineering genius is found not in a sprawling forum or a soaring aqueduct, but in the very floors and walls of their homes and bathhouses. In a world without forced air furnaces or electric radiators, the Romans engineered a system of central heating so effective, so luxurious, that it would not be widely replicated in Europe for more than 1500 years. This was the Hypocaust, a word that literally means fire beneath, and it represents a breathtakingly clever manipulation of heat and airflow that turned the bitter cold of winter into a distant memory for those who could afford it. The principle was elegant in its simplicity. A furnace or prefurnium was stoked continuously by slaves or servants, often located in an external room to keep the smoke and soot away from the living spaces. But this fire didn't just heat the air around it. Its heat was captured and channeled. The real innovation was the raised floor. The solid floor of a room was supported by a grid of short, sturdy pillars made of stacked clay tiles or stone bricks, creating a hollow space or plenum about 2 to 3 feet deep. The hot gases and smoke from the furnace were directed into this underground chamber, where they would swirl and circulate, effectively turning the entire floor into a massive radiator. The heat would then slowly, steadily, conduct through the layer of concrete and tile above, warming the room from the ground up in a gentle, even wave. But the Romans didn't stop at the floor. Understanding that heat rises, they further engineered the walls to become part of the system. Embedded within the walls were rows of rectangular hollow tubes made of terracotta, called tubuli. These box flues were carefully stacked and mortared together, creating continuous vertical channels from the hypocaust chamber below all the way up to the roof. As the hot air from beneath the floor rose, it would naturally draw through these wall cavities, ensuring that not just your feet were warm, but that the very air around you was consistently heated. This brilliant design prevented the walls from becoming cold surfaces that could condense moisture and create damp, making the rooms not only warm, but also dry and healthy. The exhaust from this entire system would eventually exit through vents in the roof or specially designed chimneys, ensuring a constant draft that pulled fresh heat from the furnace through the entire network. The most sophisticated application of this technology was in the vast public bath complexes, like the baths of Caracalla in Rome. These were not simple buildings, they were thermodynamic masterpieces. A complex series of furnaces would heat different rooms to precisely different temperatures. The frigidarium or cold room was unheated. The tepidarium was a warm lounge, gently heated by the hypocaust to a comfortable temperature. The real showpiece was the coldarium, the hot bath. This room was often positioned on the south side of the building to capture the sun's warmth, and was heated aggressively by its own dedicated furnace. The floor here could become almost too hot to walk on without sandals, and the water in the large plunge pool was kept scalding hot by a heated metal tank above the furnace, known as a testudo, or by running water through pipes that were baked by the furnace's flames. The entire process was a carefully orchestrated ballet of fire, water, and air, all managed without a single thermometer or pressure gauge, relying instead on accumulated empirical knowledge and skilled stokers. The luxury this system provided is almost difficult to overstate. In the depths of a British or German winter, a Roman patrician in his villa could stroll on warm floors in bare feet. The marble and mosaics, pleasantly heated against his skin, while the wind howled outside. The public baths offered every citizen, from the wealthy senator to the common soldier, a refuge from the cold, a place to socialize, conduct business, and cleanse oneself in unparalleled comfort. The fuel cost was enormous, requiring vast quantities of wood or charcoal, which made the Hypocaust a powerful symbol of status and wealth. Its eventual disappearance, following the fall of the Western Roman Empire, stands as a stark indicator of the loss of that complex technological knowledge and organized economy. For centuries afterward, European winters were endured huddled next to smoky, inefficient open fires. The memory of evenly radiated heat fading into little more than a legend until the modern era rediscovered the very principles the Romans had mastered so long ago. So we arrive at one of history's most tantalizing what-ifs. We've seen the Romans conquer materials, water, and force with breathtaking ingenuity. But did they ever stand on the precipice of a completely different kind of revolution? The question often arises, with all their mechanical genius, did the Romans ever discover steam power? The answer is a fascinating and nuanced one. A story not of a failed invention, but of a brilliant toy born into a world that had no need for it. The evidence for their knowledge of steam's potential is undeniable, and its name is the Pile. While often attributed to the Greek engineer Hero of Alexandria, it's crucial to remember that Hero lived and worked in the 1st century CE, a time when Alexandria was a thriving center of Roman learning and culture. His device was not a secret scroll or a myth. It was a real, functioning machine described in his published works. So what was it? Imagine a sealed cauldron of water placed over a fire. Rising from this cauldron are 2 pipes that channel the steam into a hollow sphere, which is free to rotate on an axis. 2 more small pipes, bent at an angle, protrude from opposite sides of this sphere. As the fire boils the water, steam rushes through the pipes into the sphere and violently jets out of the L-shaped nozzles. And here's the magical part. According to Newton's 3rd law, every action has an equal and opposite reaction. The force of the steam shooting out one way causes the entire sphere to spin rapidly in the opposite direction. It was, without any doubt, a working steam turbine. This is where the modern mind reels. They had it. They understood the core principle of jet propulsion and rotary motion from steam. So why on earth did they never connect these dots to create steam engines, locomotives, or factories? The answer lies not in a lack of intelligence, but in a completely different economic and social reality. The Roman world was built on a foundation of abundant, cheap, and expendable human labor: slavery. The economic incentive to develop machinery to replace muscle power was virtually non-existent. Why would a Roman estate owner invest a fortune in developing a complex, finicky, and fuel-hungry steam engine to grind grain when he could simply purchase another 100 slaves to push millstones? The cost-benefit analysis was completely inverted compared to 18th century Britain, where rising wages and a shortage of labor created a powerful incentive to mechanize. Furthermore, the materials and precision engineering required for a practical, large-scale steam engine were simply beyond even the Romans' formidable capabilities. The Pile was a demonstration model made of bronze. A working industrial engine would have required massive, perfectly machined iron cylinders, pistons with tightly fitted seals to contain high-pressure steam, and advanced valve systems technologies that were millennia away. The metallurgy alone would have been an insurmountable hurdle. Their iron was not strong or consistent enough to safely contain the tremendous pressures needed for useful work without catastrophic explosion. Hero's device was a low-pressure toy. Scaling it up was a problem of an entirely different magnitude. Perhaps most importantly, the Roman mindset itself was a factor. Their engineering was profoundly practical and immediate. They excelled at solving clearly defined problems. How to bring water to a city, how to span a river, how to lift a heavy stone. The Eolipile, however, was what the Greeks called a thaumato, a wonder, a marvel. It was a device intended to inspire awe and demonstrate philosophical principles, not to perform utilitarian labor. It was likely used in temples to mystify worshippers, or in the homes of the wealthy as a fascinating conversation piece. The intellectual leap from a philosophical demonstration to an industrial prime mover requires a specific set of circumstances, a pressing economic need, a certain scientific worldview, and a culture of innovation geared toward productivity. The Romans, for all their brilliance, existed in a world where that particular combination of factors had not yet aligned. They held a spark of the future in their hands, admired its cleverness, and then set it aside, never fully realizing they were looking at the key to a revolution that would have to wait for another 1700 years. From the self-healing concrete that defied the sea to the soaring arches that captured the very sky, from the hidden hypocausts that warmed ancient homes to the intricate machinery that powered their colossal spectacles, the breadth of Roman engineering is nothing short of breathtaking. We have walked the roads they surveyed with impossible precision, marveled at the aqueducts that leaped across valleys, and stood beneath the dome that still defies gravity. This was not merely construction. It was a profound conversation with the forces of nature, a demonstration that human ingenuity, when paired with unwavering ambition, could shape the world for millennia. The true legacy of these secrets, however, is not just in the silent stones we admire as ruins. It lives on in the very bones of our modern existence. Every time we drive through a tunnel excavated from opposite sides that meets in perfect alignment, we are utilizing their surveying principles. When we rely on a complex network of pipes to bring us clean water and carry away our waste, we are living in a world they engineered. The grid patterns of our cities, the very concept of public infrastructure as a civic right, and the enduring pursuit of building materials that can stand the test of time, all of these are direct descendants of the Roman worldview. Their innovations were so foundational, so deeply embedded in the logic of civilization, that we often use them without a second thought, their ancient origins hidden in plain sight. This journey through their secrets reveals a people who looked at a challenge not as a barrier, but as an invitation to innovate. They saw a river and built a bridge not just to cross it, but to declare their mastery over it for all time. They gazed upon a barren landscape, and with a web of dams and reservoirs, convinced the desert to bloom. Their story is a powerful reminder that progress is built on a willingness to experiment, to learn from empirical evidence, and to invest in a future you yourself may never see. They built for eternity, and in doing so, they left us not just with monuments, but with a timeless blueprint for resilience, ingenuity, and the audacious belief that no problem is too great to solve. Now, I'm incredibly curious to hear which of these Roman marvels captured your imagination the most. Was it the mystical concrete that grows stronger in seawater, or the terrifying precision of their siege engines? Perhaps the sheer logistical genius of their nightly fortified camps, or the serene acoustic perfection of their theaters? Let me know your favorite down in the comments. I read every single one. And if you enjoyed unraveling these ancient mysteries with me, make sure to subscribe and hit that bell so you don't miss our next adventure into the past, where we'll continue to uncover the astonishing secrets left behind by history's greatest